So when we previously left off, we were talking about mass-specific angular momentum. This time, we're going to talk about flight path angle, which is typically denoted as the lowercase gamma. Now, I would like to take a moment to address something that I'm sure some of you here may have probably already noticed by this time. It's that I tend to, when I'm wanting to be fancy with my handwriting, or when I'm writing really fast, sometimes I will write my R's like that, I will write my V's like that, and I will write my gammas like that. You already see the problem, don't you? These are three distinct letters and variables, and they are not the same. I will try to write my variables a little more neatly so that you'll be able to distinguish them from one another. Failing this, I can always edit, and if it becomes a really big problem, let me know in the comments and I'll see if I can come up with a way to address it. Now, circling back around to the topic at hand, if we have a host body, like the Earth, doesn't have to be the Earth, but it can be, draw an imaginary line straight up to our spacecraft. We can see that at a 90-degree angle to that vertical, we have the horizon. If we transpose that all the way up to our satellite, we have something called the local horizon. And let's go ahead and put in some important features here. That's not supposed to be a triangle, that's supposed to be a hat. U, theta, hat. There we go. So, why am I telling you this? Well, if a satellite or an orbiting body were moving in a circular orbit, it would only ever have velocity in the tangential. It would only ever be moving tangent to the local horizon. In nature, more often than not, you will not see that. You will see it in an elliptical orbit, where half the time it is moving away from the host body, and half the time it is moving closer to it. Figure that out. This angle in here is our flight path angle. So let's blow that up down here, make it a little bit easier to see what's going on. There's our V. Here's our tangential. And there is our radial. And once again, that is in here. So we'll move this all the way down. Now, if we want to solve for gamma, we want to know what our flight path angle is. Well, if you're very serious about this material, I assume that you have a good grasp of your trigonometry at this point. So we can see, and there's at least two different ways of doing it. But I'm going to use that variable specifically. So we want the cosine gamma equal to the adjacent over the hypotenuse. Yes, I have a master's degree in aerospace engineering, and yes, I do still need that little helpful mnemonic thing. SOHCAHTOA, lifesaver. So, oh, well, there you go. That's how you can derive it. But it's perhaps a little more useful to know what our tangential speed is, which is why I chose it. And honestly, it really is that simple. So let's do a quick example on this. And just put that here. Example. So we're going to use the same values as last time, where we had our radius being 16,365.424. Double checking my notes to make sure I copied it down right. I did. I'm great. 0 and 0. With, again, these two should always be 0. If they're not, no, change the angle that you're measuring at. It's honestly easier to do it that way. Kilometers. And our velocity is 0.4556, 5.3455, and 0 kilometers per second. Yes. All right. Before we can plug it in to our equation up here, let's do some basic housekeeping, because we have vectors here, we want scalars. So let's do this. Well, again, we only have the one value in here, so it should be easy enough to work with. Underline that to make it distinguishable. Velocity is slightly more tricky because we actually need to use Pythagorean's theorem on this one. Weird. Almost didn't budget enough room for me. Almost. Getting better about that. All right, so plug it into our calculator here. There you go. There is our velocity. So if we want to solve for gamma, let's go ahead and do that. So gamma is equal to E tangential over V. We have, no. Carefully. Now we get to plug things in. We have V theta, which is that particular component. Let's try that again. We have 5.3455. And we have our total, which is going to be that component. 5.364880391. And by now you should see why I like putting in all the digits for my intermediate steps, because just including the two decimals here is going to leave out a lot of information, especially when the numbers are as close together as they currently are. Using all of them, it's kind of nice because it gets me a more accurate number. So let's plug this in now. 4.87 6. There you go. That is our flight path angle. Alrighty, so we just found what our flight path angle is, but I have a question for you. So, is our satellite moving away from the Earth or towards the Earth? It turns out the cosine equation here that we've been using does not carry that information through, but the information is provided. In fact, it is provided right there. That radial component of our velocity is positive. Positive in this context means that it is moving away from the Earth. Therefore, we have a positive gamma. Where instead that value negative, we would have a negative gamma. It's also worth noting that if we were to use the tangent instead, I'll just write this down here. Opposite VR, adjacent to the theta. That information would be baked into our equation. It would make it into the final product. We wouldn't need to worry about that as much as we do now with the arc cosine. So just keep that in mind as you go to use this equation in the future. And that could be the end of the video, except I want to point something out. Let's go over here. Let's go back to our previous video where we saw that because we only ever have a radial component to our radius, as the name suggests, and never a tangential component, we really don't care what the radial component of our velocity is when we are determining our specific angular momentum. So because of that, we only care about our tangential velocity. So another valid way of writing it, let's just bring that equation back over here. R cross V. And that's in vector form. If we were to turn this into a scalar, H is whatever our R is, and we only care about V theta. Well, quite conveniently, we wrote our flight path angle in terms of V theta. So let's go ahead and write that in, and actually let's bring this. I'm gonna have to scroll back. No, I won't. Oh, I have notes. So we have our angular momentum is equal to our radius, 16,065.424 times our overall velocity. Let's keep that in frame. 6, 8, 3, 1 times the cosine of 4.8716 degrees. Now, already I'm doing a bit of a no-no here just because I would be treating this as an intermediate step, and I have already rounded off the decimals. But since this is just a proof of concept for you guys, hopefully you'll let me get away with that. 5.54. And I shouldn't be off by too much, assuming I did this right. 87,481. kilometers squared per second. And so let's check back over here. We should be rather close. Look at that, 87,481 kilometers per second. And that is the magic of the flight path angle. And quite fortunately, I didn't have to be wrong on the internet. And you got to see me write an equation right in here, which is good to have boxed, by the way. You got to see me use an equation that used all three of my tricky variable letters, and I was able to distinguish them. Well, that's all I have for today. Stick around for the next episode. Thanks for stopping by.